Every function you've studied takes an input and gives you an output. An inverse function reverses that exact process. The output becomes the new input, and the original input becomes the new output. This graph shows the linear function f of x equals 2x minus 1. To find the formula for its inverse, we take the algebraic step of swapping the variables. We replace f of x with y, swap the x and y to get x equals 2y minus 1, and then solve to make y the subject. Add 1 to both sides, divide by 2, and we get y equals x over 2 plus 1/2. When we map the original line on the left and plot the new equation on the right, we can see how the coordinates relate. A point on our first line maps directly over to its swapped counterpart on the new line. Look closely at what happens when we place these graphs on the same set of axes. Swapping x and y algebraically creates a perfect reflection geometrically across the diagonal line y equals x. Every coordinate from the original graph reflects directly across this dashed line, swapping its position from x:y to y:x. The algebra and the geometry are describing the exact same relationship. Calculating an inverse physically mirrors your data points across the y equals x axis. This is a downward opening parabola, representing the quadratic function g of x equals negative x squared. It passes straight through the origin at 0, 0. We apply the same algebraic process here. We swap the x and y variables to get x equals negative y squared. To solve for y, we divide by negative 1 and take the square root. This leaves us with y equals plus or minus the square root of negative x. This graph shows the original parabola in black and its reflection across the y equals x symmetry line in red, creating a sideways curve. But this presents a mathematical problem. A vertical line test intersects the red graph in two separate places at once. Because a single x input on this new curve maps to two different y outputs, the inverse of a full parabola is not a mathematical function. To fix this and create a valid inverse, we have to restrict the domain of the original parabola. We do this by slicing it exactly at its axis of symmetry. This gives us two separate halves, one where x is less than or equal to 0, and one where x is greater than or equal to 0. Let's isolate just the negative side of the parabola, where x is less than or equal to 0. Take a second to pause the video and visualize what this single curve will look like when reflected across the diagonal. When we reflect only that restricted domain across the line y equals x, we get a single functional arc. It intersects the original curve at 0, 0 and negative 1, negative 1, and easily passes the vertical line test. This reveals a strict rule for these reflections. The domain of your original function explicitly becomes the range of your inverse, and the range of the original becomes the domain of the inverse. This image displays the exponential function h of x equals 2 to the power of x. It is shown by its sweeping upward curve passing through a y-intercept of 1. Following our rules, we swap the variables to get x equals 2 to the power of y. To make y the subject when it is an exponent, we must use logarithmic notation. This strictly rearranges our equation into y equals log base 2 of x. Here we see the original exponential curve in black, its logarithmic inverse in red, and the dashed line of symmetry. The original function's horizontal asymptote along the x-axis reflects as well. It swaps variables, standing up to become a vertical asymptote along the y-axis. The inverse of an exponential function is always a logarithmic function. Because this resulting curve inherently passes the vertical line test, it requires 0 domain restrictions. To tackle inverse problems accurately, focus on 4 operations. First, algebraically swap your x and y variables and solve. Second, apply that exact swap to your coordinate points. Third, verify your work by reflecting the graph over the y equals x line. And fourth, if you are working with a many-to-one function, like a parabola, strictly restrict its domain first. Mastering the symmetry of the y equals x reflection allows you to map linear, quadratic, and exponential functions consistently across every exam paper.